What is time dispersion? Time dispersion is broadening of pulse as the signal is transmitted through the channel. As the signal spreads over time, it might overlap with other signal. In that kind of case, it causes ISI, intersymbol interference. That phenomenon of spreading of pulse or broadening of pulse or signal is called as time dispersion. We can study time dispersion by using these 4 parameters: minimum axis delay, maximum axis delay, mean axis delay, and RMS delay spread. We get these parameters from a characteristic called power delay profile, short form PDP. This graph is my PDP. It is a characteristic between received signal strength, which is usually shown in dB, decibel, in y-axis, and axis delay, shown by usually tau, or the unit will be microsecond or nanosecond. Right now in this case nanosecond, but it will be microsecond. If it is indoor, it will be nanosecond. It will be, if it is outdoor communication, then it is microsecond. So PDP shows your signal strength for different instant of time. Now, as the receiver receives this signal, it also receives some noise or distorted signal which is embedded inside these signals. So PDP also shows some noise which is included inside this received signal. So in that case, we need a thing called threshold. If the received signal is below this threshold, we will take that as a noise. In this case, in the first case, I have taken minus 10 dB as the threshold and minus 20 dB as my second case threshold. Now let's get this. What is this minimum axis delay? Minimum axis delay is an axis delay, okay, that corresponds to the first peak when the received signal goes beyond the threshold. In this case, right now, this is my threshold. And which is the first peak? This is the first peak. Which is the corresponding axis delay? This one, nearly 0. So this is my minimum axis delay. What is maximum axis delay? Maximum axis delay is the axis delay which corresponds to the last peak before the received signal goes below the threshold. What is the threshold? Minus 10 dB. This is the peak, last peak before it goes below this threshold, and this is my corresponding axis delay. This is our maximum axis delay, and usually it is calculated. Your maximum axis delay is calculated by a formula is tau k minus tau 0. What is tau k? Tau k is this value and tau 0 is this value. So tau k, tau x minus tau 0. This is tau x and this is tau 0. So what is tau x? Tau x is the maximum delay at which the multipath component is within x dB of the strongest arriving multipath signal. What is tau 0? Tau 0 is the first arriving signal. Which is the first arriving signal? This was the first arriving. That's why there is a peak. Okay. Always these peaks are the arriving signals. First arriving signal is tau 0. So this is how you calculate your maximum axis delay. Your mean axis delay is denoted by a formula that is tau bar will be equal to summation a square k tau k divided by summation tau k square summation ak square. Now, mean axis delay is the moment of the power delay profile given by this formula. Summation of ak square tau k divided by summation of ak square. Now what is this ak? Now I told you in the last class that any of your received signal can be represented in terms of your impulse response. So from this PDP, I can show this PDP in the form of impulse response as well. So let's say these are your impulse response. Okay. This is also PDP graph, but in the form of, I'm showing this as impulse response. Okay. Let's say this one is P tau k, this one is tau k. So for different instant of time, that is tau 0, tau 1, tau 2, tau 3, this is your axis delay, this is your received signal. And for every instant of time, let's say for example at tau 0, I have the amplitude A0. At tau 1, I have amplitude A1, A2, and A3, whereby k will be equal to 0, 1, 2, 3. Now, okay, now if I have to calculate the mean axis delay, that is tau bar, for this power delay profile, I will say a naught square dot tau naught plus, because there is a summation here, plus a1 square tau 1 plus a2 square tau 2 plus a3 square tau 3 divided by summation of ak square, that means a0 square plus a1 square plus a2 square plus a3 square. And there is a formula that is your energy is equal to your energy square equal to power. Here energy is in terms of amplitude square. So this formula can also be written as summation k p tau k into tau k divided by summation p tau k. So this formula I can even write as p tau 0 into tau 0 plus p tau 1 into tau 1 plus p tau 2 plus p tau 3 into tau 3 divided by p tau 0 plus a1 square is p tau 1, a2 square is p tau 2, tau 3. So this is how we get your mean axis delay. So we get a value, and let's see, suppose that value is somewhere here, and that point will become your C. This is your mean axis delay. This part will be your mean axis delay, which you have got using this formula. Now RMS delay spread. What is this? RMS delay spread is given by the formula sigma tau. Sigma tau is given by the formula tau square bar minus tau bar whole square. This is the formula for your RMS delay spread. What is this? This is your mean axis delay. What is this? The formula of this one will be given by summation k ak square tau k square divided by summation k ak square be equal to summation p tau k square divided by summation k p tau k. Similar formula to this one, but just I have square here, right? Square. There is a square here. Square. Everything is same. Okay, so how we'll write this formula? P tau k in tau 0 square plus p tau 1 square plus p tau 2 square plus p tau 3 into tau 3 square divided by p tau 0 plus p tau 1 plus p tau 2 plus p tau 3. This will be your formula for this part, which is the first part. This one, so with using this formula, we'll get the RMS delay spread. Okay, so RMS delay spread, it characterizes time dispersiveness of the channel, which is obtained from power delay profile. It indicates delay during which the power of the received signal is above a certain value. So in this case, let's say your RMS delay spread is this region. This region will be your RMS delay spread, which is between your mean axis delay and your maximum axis delay. Okay, so minimum axis delay, maximum axis delay, mean axis delay, they are the instant points of axis delay. They are the points in the axis delay. But RMS delay spread is the range of axis delay, is the spread of axis delay between your mean axis delay and your maximum axis delay. So let's take one example, one numerical, that is example 1, which will make it more clear. Let's say this is your given PDP. Okay, this is in tau is in microsecond. Okay, and this is your amplitude. One is 1 at 0 microsecond, 2 microsecond your received signal is 0.6, and at 4 microsecond your received signal is 0.3. So you need to find your sigma tau. Okay, to find this sigma tau. So to find this, we have a formula that is root of tau square bar minus tau bar whole square. So how to find tau bar, which is your mean axis delay, summation p tau k into tau k divided by p tau k summation. This will be equal to 1 into 0, this is p tau k into tau k, and now since this is summation, I'll go plus, right? 0.6 into 2 plus 0.3 into 4 divided by 1 plus, right, 1 plus 0.6 plus 0.3, the value is 1.26 microsecond. So your mean axis delay is 1.26. and what about your tau square bar? Tau square bar, we have formula, this formula, okay, and we write 1 into 0 square plus, okay, 0.6 into 2 square, okay, plus, because it is tau k square, remember that, so that's why I'm squaring the tau k values, which is 0, 2 and 4, plus 4 0.3 into 4 square divided by 1 plus 0.6 plus 0.3, because it is p tau k. P tau k values are 1, 0.6. This will come to a value 3.79 microsecond. And your sigma tau, I can conclude that root of, I get this from this formula, okay, this particular formula and this formula, 3.79, which is your tau square bar, minus tau bar. What is tau bar? 1.26 square, remember? So 1.26 square, that is coming around 1.48 microsecond, will be your RMS delay spread for this question. Okay, let's look another example. What if your received signal strength is in terms of dB? This is example 2. Let's say minus 10 dB, minus 20 dB, minus 30 dB, and this is your, okay, two values. This one, okay, and this one is 0, and this is in dB. Your p tau k is in dB now, and this is in microsecond, okay. This is 5, this 1, this is 2, say this is 0, 5. Now I need to find sigma tau. I need to find mean axis delay for the threshold minus 10 dB. Okay, I need to find sigma tau, and I need to find maximum axis delay for the threshold minus 10 dB. Okay, now for this graph, what is your minimum axis delay? So this is your minimum axis delay. Okay, it is axis delay correspond to the peak, first peak, when it crosses beyond the threshold, which is 10 dB, this is your threshold, or whether it touches or it crosses that peak, and that corresponding value of axis delay which corresponds to that peak, which might touch the threshold or crosses beyond that threshold, that is called as your minimum axis delay. In this case it is 1. So your minimum axis delay is 1 microsecond, and your maximum delay is, which goes beyond last nullo, that is 5, the last peak before it crosses the axis delay. This is 5 microsecond. This is your tau naught, this is your tau x. So maximum axis delay will be given by tau x minus tau naught, that is 5 microsecond minus 1 microsecond, that is 4 microsecond will be your maximum axis delay. Now what about your sigma tau, root of tau square bar minus tau bar whole square? Okay, now how to find tau bar? Summation, what is that? Summation of p tau k, okay, into tau k divided by summation p tau k. So how to find? We'll not take directly because this is in dB, so we need to convert this into linear scale or normal scale. Okay, how to convert that? 10 log x will equal to minus 10 for this case, right? What is that? X equal to 10 to the power anti-log of this minus 10 divided by 10, that will come around 0.1. So in this case we'll do for all these values, this will come as this will be 0.1 for 10 dB. This one will be 1, 0 will be 1, this is 0.1, this one will be 1, this one will be 0.1, 0.1. What about this one? This one will be 0.01 if I take the anti-log using this formula. So there, from there you can calculate, and after the calculation what value will get? Tau bar will come as 4.38 microsecond. You can try yourself, 38 microsecond, and sigma tau comes around 1.37 microsecond. Okay, and you need to calculate for this, you need to calculate this value also, right? So tau square bar, that formula is there, and it is square this is tau k square divided by summation of the tau k. Okay, so we end our lesson of time dispersion parameter here, and this tau k has a very important significance. From this tau k we can find your coherence bandwidth, which we'll see this in the next class.